There are more of you here today than I was expecting because of the nice weather. Figured you would have waited till night to watch the video or something and like enjoyed the nice weather. But I'm glad you're here. This is great. Do you realize we only have like 3 more real lectures? Today, Wednesday, next Wednesday, because next Monday is Marathon Monday, so we're no class next Monday. And then Wednesday is our review one. So really, we've got like 2 more. Depending on how much we get through today, Wednesday's lecture may be on Comp 40 preview. Like for those of you who are going to take Comp 40, I don't expect or require. Well, I don't require any of you guys to come at all. But if you wanted to leave on the comp, like not come to the Comp 40 day, and you weren't going to take Comp 40, I'd be fine with that. Although we do some interesting things, I think. If we don't get through quite as much today, I might push the Comp 40 lecture to like the Monday, or rather maybe the Tuesday after the final, which is the day after the final. And you do not have to come to class. What I'll do is I'll tape it and put it online, but you can do that. So we may, depending on how much we get through today. All right. Here's what we're going to do today. So I'm calling this the Esoteric Data Structures Day. We're going to hopefully go through 3 different data structures today, and we're going to kind of like go not too deep into any of them. But they're data structures that many people don't actually know about because they're somewhat rare. And not only are they somewhat rare, well, what that means, being somewhat rare, is that A, they're useful. Like at least I think all 3 of them have very interesting uses. But in addition to that, they're the kinds of things that if you whip them out on an interview question, people will be kind of impressed, right? If someone says, "What would you do in this case?" and you say, "I think I might use a Bloom filter," they'd go, really? That's a good answer. So these are the kinds of things that you might see. You probably wouldn't get specifically asked in an interview, although you might. But if you didn't and you kind of figured out, oh, this is the kind of situation I might use that, kind of a good answer. OK? First things first, before we go into the esoteric data structures, Boggle. Questions on Boggle. I have not put Provide up yet. By the way, I don't think Provide's really going to do much testing. It might do kind of basic testing, but not much more than that. Any questions on Boggle? It's going all right? People who haven't started it yet, you're crazy. For everybody else, hopefully you're doing OK. I know some people who have actually finished the problem already, but that's OK if you haven't. But it's kind of intense. But it's going OK? So far, so good? No questions about it? Piazza's been fairly busy with questions. So if you first place to look would be there. First place to ask your questions, obviously, there too.
Oh, wait, yeah.
Question. 1 sec.
Are you allowed to use the vector class for other things besides BogLetter?
Yeah, you can use the vector class for other things besides BogLetter. I'm happy to use it wherever you want, where you would use another dynamic array. The other data structures, there's a Piazza post that came up about other data structures. If you're using it for the main program, you kind of have to create your own. I'd like you to create your own. If you wanted to go above and beyond, use whatever you want. Like I'm happy to use whatever you want. Yeah?
If someone were to enter the same word twice,
yeah.
And when it checks it, should it print out like 1, OK, yes, or OK the word, and then 0, OK that word, or just be 1, OK that word?
Yeah, very good question. OK, here's the question for everybody. If someone types in the same word twice, now for the solver, you need to find all the possible words. So you may get duplicates because there's 2 letters that are next to each other that would have duplicates. For the checker, if someone types in top and then I don't know pop and then top again, right? This one should be OK. This one should not be OK. It should actually be a no. OK, and then the scoring should go like that. So you should keep a list in the checker to say, hey, have I seen this word before? OK, you can do that with a try might be a good idea, another dictionary, or vector if you wanted to, but dictionary is probably going to be faster in that case, right? But so the output of this, if top and pop both occurred in the Boggle board, the output of this would be, let's see, you would have, for top, you'd have OK top, you'd have OK pop, and you'd have no for the second top. And then in the scoring, it would be, what is this, 3, 3, and 0. So that's the way it should show up on your output. Does that make sense? OK, yeah?
Would that be only if there's only one instance of the top and bottom?
Even if there's only one instance.
But if there's multiple instances?
You don't get points for multiple instances. No, not even in the real Boggle. Yeah, even if you can make the same word in 2 different ways, you only get points for 1 word. This is the way Boggle works. Your house works different. House rules, right? OK, anybody else? All right, good. Manageable assignment, though, overall, so far? Nobody's freaking out yet? Got a little time. OK. All right, let's talk about these other kind of interesting data structures. We're going to start with this thing called the skip list. And I think you'll find it interesting based on what I've said about lists in general in the past. Then we're going to go into this really interesting one called Bloom filters. This one is going to be our first probabilistic data structure. Although I should say, in the skip lists, we're going to deal with probability as well. In fact, we're going to deal with this coin in a little bit. Remind me that it's right there. And then this other thing called ropes, which are an interesting way to deal with text documents. So we'll go into that. So let's go to skip lists. So you guys all know that I'm not a big fan of linked lists, right? Not a big fan of linked lists. I've been saying that since the first day of class. And there's lots of reasons why I'm not a fan of linked lists, right? They're slow. They're terrible for caching. They're node-based. So you got a lot of things to deal with when you're programming them, et cetera. But let's talk about some of the other problems, right? I just listed a whole bunch of problems with linked lists. If we have a sorted linked list, does that do anything for us? Like, can we do a better search or anything if we have a sorted linked list? It doesn't do anything for us, right? Like, there's no way to go through a sorted list. Could we help out a sorted linked list somehow? OK, let me give you an example. Let's say that we had a linked list that looked like this. Let's say we had a linked list that was sorted. Let's just say it was sorted. 10, we'll make it a doubly linked list. And then 15, and then double, and then say 16, and then, oh, I don't know, 80. Right? No. OK. So if we have this doubly linked list like this, can we do anything else? Actually, let me add one more, just to make it an odd number. Maybe that'll be a hint. 100, like that. Is there anything we could do to make searching through this list a little bit better? Think about that for a minute. In fact, talk to your neighbors about that. Before you answer, talk to your neighbors about that. Is there any way we could do anything we could do to this to make searching through it a little bit better? Did you already look at the notes? No? You what? When I gave you the what? Well, yeah, maybe. Maybe I gave it away a little bit. OK, what do you guys think? Gabrielle, you had something. I saw you talking pretty intensely there. What did you think? Yeah. If you make it OK, if you make it a circular list, that might be. You might not end up being able to go either direction. You don't. And I guess you could tell which direction by doing what?
If you make the head the middle.
Oh, if you make the head the middle. OK, was this what you were going to say, Kalina? Something about the middle? Yeah, but if you did make it circular, at least you'd kind of be able to, if you're at 16 and you're looking for 70, we know which way to go, right? Because it's sorted already. So we know we could go that way. And if you only had to go to the end, maybe you could wrap around. That wouldn't be a bad idea. Now, what were you saying about the middle? I liked what you were saying about the middle. Oh, OK. So make something the middle there. OK, maybe the middle isn't important because at least then you'd be able to do what? Be able to search either way, OK. I mean, I guess in a circular list, if it's a circular list, the head and tail don't really exist in the big picture, right? It doesn't actually matter. So that might not be. But I like the way you're thinking, Yuki.
So in terms of like searching through the entire linked list, unless you have like a pointer to every single node, like is it impossible to have like an n log n like search?
Well, we're not getting. Well, we may get to an n log n something at some point, but not really an n log n is probably what you're thinking, right? A log n search. Yeah, we might get to something like that. Cleaning out your hand up and then.
you wanted is greater than the one in the middle, then just start
Uh-huh.
in the middle and search down.
Okay, yeah. I put head over 2. I meant like something like the list, the length over 2 or something like that. So maybe you could at least speed it up by half if you were able to check the first one and the middle one. Okay, now you were saying, sorry, were you saying about the?
Yeah, I was going to say like, if you put a pointer on each node pointing to like the middle to the end, from that point to the end, you could keep jumping between the middles.
Yeah, so we would have to add more information, but maybe there's some way to have something where we're going somewhere down the list and doing that. But yeah, the point about, hey, if you tried to have a link at everyone, it's not going to do you. I mean, you're going to be like duplicating too much effort there, and you're not really getting that much of a benefit. Why not just do it in an array? Nathan?
One interesting thing that you could do, which would halve the search time, would be to give each node a pointer that points 2 elements ahead. And then as soon as you find one that's greater than the value you're searching for, you only need to check one more. So when you're scanning through, it's twice as fast. And then when you get above, you need to check one extra element.
I see. So you're gonna basically jump by half each time. That's not a bad idea.
So in that, if you're looking for 80, you only have to check 10, 16, 100. That's too much. You go back one to check 80 instead of going through 15, 16.
Right, and if there were many more in there, you'd do that. But then you're gaining 2 on each one, maybe. Yeah, you're definitely gaining half once, more or less, I guess overall. Yeah.
Just out of curiosity, is there a data structure out there where you get random access and you can also add and delete at constant behavior?
You get random access and you can add and delete in constant time. Not really. There's not really a data structure in particular that you can do that. No.
That's not the problem with both.
Yeah, that is the problem with both. Right. We're trying to kind of figure out if we're going to be able to get the random behavior of like an array, but then have a linked list where you can add and delete constantly. By the way, you're not going to be able to add and delete in this at constant time because you're keeping it sorted. So there is an n squared or and linear factor there as well. But we're getting there. We're getting there. Now, I like the way we're thinking. So if we did put the halfway point there, so good job for everybody thinking that. If we did put a halfway point there, this would be partially, this would help out like in one instance. If you skipped every other one, you'd get a benefit going many larger distances. So that's something like that. But let me go through something that we can do that's kind of more interesting as it turns out. Does anybody recognize the ordering of these numbers? Yes, they're in order, but does anybody recognize this ordering? Emily, I'm looking at you, by the way. Emily, what game was on TV last night? Baseball. Who's playing? Okay, the Yankees, Red Sox, and the bad guys won, unfortunately, last night. Thinking along the Yankees, Red Sox, if you think about like the city you're from, do these numbers make any sense to you?
Are they players?
They're not players. It's not baseball, but it's about where you're from.
Are they like streets?
Ah.
And famous streets near.
Oh, who said it? What are they? Are they any particular line? Subway stops?
1 to 3?
No, I don't think it's 1, 2, 3. I think it's the 7th Ave. Is that the 1, 2, 3? Okay, so these are New York City subway stops. They're no other numerical like that. They happen to be streets on there. You can go from 14th to 23rd to 34th to 42 to 50th. But you wouldn't do that most of the time, would you? What would you do if you were in New York City? Who else is from New York City? Anybody? A few people. Okay. If you were in New York City, would you get on the 14th, go to 23rd, 34, 42 if you were going all the way to 66? What would you do? Okay, you would take the express route. Right? There's an express route. In fact, I guess 66 was the wrong answer. You probably couldn't do that. You'd have to, well, you could, but then you'd have to get off. But if you wanted to get somewhere down the line, New York is interesting. Unlike the T, the New York subway system has these express routes, which they have 4 tracks associated with them, right? 2 in each direction. One track is responsible for the regular local traffic, which would be all the stops at the bottom here, right? The other one is responsible for the express stops like this. This models almost exactly a skip list, almost exactly. Okay, here's what a skip list is. Take the idea of finding some place in the middle but do it not just in the middle. So it's kind of a hybrid of what Nathan was saying and what you other guys were saying about but put something in the middle, right? Take an express route to go through the numbers in a different list. What you have to do here is you have to create a second linked list. Okay, and the second linked list is your skip list. We're skipping a bunch of stops on the subway, okay, because you don't want to have to get down here, right, and do all these stops if you can know you can do the ones up here. Now, you can't necessarily do that automatically. If we wanted to go to 59th Street, right, what's the most efficient way in this case? If you knew what you were doing. 14th to 34th to 42nd, get off the express, go down to the local, and go all the way to, did I say 59th? Go to the 59th Street. Right? So that's the way you do it. The problem with a linked list is you don't, and if it's sorted, you don't know if the next link is necessarily bigger or smaller, but you can check. You can say, what's the next link's number? And if it's greater than the one you're looking for, get off the express. Right? This is how a skip list works. It's actually pretty clever. By the way, did I tell you we're going to do a little calculus today? Haha. It's like the only time in any computer science class you'll ever do calculus is like in the next 5 minutes. So, and it's the easiest calculus problem you'll ever do. Okay? All right. So this is how you do. This is what you do. You basically go, if you're searching through here, list 1 is the one with fewer stops, the express, we'll call it this. List 2 is the one that has all the stops. Now you definitely need a list with all the stops in it. Right? You need some way to go to all the numbers. If you're talking about a subway, you need one which goes through everybody, right? I mean, I suppose you come up with some weird hybrid where you always know to get off and it only it won't go the next ones. But we're always going to have one list which is going to be our linked list, which we all love to hate, right? But we're going to augment it with another list. Okay, so if we were going to go to, I guess it was 59, you'd go all the way down. In the big picture, you'd at least check 72 if you don't go there. But you'd somehow backtrack. How do we backtrack in a linked list? Keep a previous and next, or just make it a doubly linked list. Probably a doubly linked list is the easiest way to do it. Or just check the next. First check if it's not null, and then check the next value, and don't go there, just go down. So you're going to have extra links on this top link, right? The top link needs to go to the next one and the equivalent one right below it so that it can get to the next one, right? I suppose there's probably a way you could have it cheat a little and go to the next one from there to there. But let's just, for now, to make it a little clearer, just have it go directly down to the one right below it. Okay, and that's how you do this searching through it. So this is actually kind of interesting. We've actually helped our linked list, especially if it's a sorted linked list, to do some things, right? Now, the question really is, how do we place the nodes in here such that we get good behavior? Because really, now the New York City subway, when they figured this out, they probably knew roughly how many people in 1907 or whenever it was created. The T's older, by the way. They probably had an idea of basically which stops made sense to have the big stops at, right? The express route. And so they go 34 to 42 is also express and so forth. But this is probably not the best spacing for a real skip list, right? What would a good spacing be? Yeah, some sort of distributed list, right? Nice and equally spaced, right? But so we want to equally space it out. So we might not have the 42 here. We'd probably put it at the 59 or something, where it's roughly equally spaced. Okay, you can figure out pretty much exactly equally spaced if you know how many are in the big list. Okay, but we're going to try to minimize these, like the number of stops up there. Okay. The search cost to go through this list is equivalent to, when I put these double bars on either side, that means the number of nodes, okay? It's the cost can be represented by the number of, and this is kind of worst case, the number of nodes in the top list plus the number of nodes in the bottom list divided by the number of nodes in the top list. Think about why that's the case. In the top list, you go a certain distance until you know to go to the next list, right? And then you basically go an equivalent distance of like the number to the next one in list 1 again, because you're not going to have to go any farther, right? You know that if you're at 42 and you check, and if you're at 42 and you're checking for 59, you know that you don't need to go all the way to 72 once you check and say, oh, 72 is the next. I'm not going to have to go any farther than 72 down here in the bottom list if I'm looking for 59, right? And if we equally space them out, that's basically like the number in list 2 divided by the number in list 1 is how many stops are in between each one in list 1. Does that make sense? Number of stops in list 1 will divide up the number of stops in list 2. OK? All right. So if we do that, right, let's do a little calculus. You guys know how to minimize some things, right? Let me rewrite this. OK, let me rewrite this. We have up here that the search cost can be represented by the number of links in L1 in the top list, right? Plus the number of links in the bottom list divided by the number of links in the top list. OK? All right? Which we can rewrite these with some other digit. Let's not like the L1 and L2 business. Let's just rewrite it like this. X, which we'll say is the number in L1, right, plus n divided by x. OK? Can you minimize that with respect to x? I bet you can. Try it. Who hasn't done calculus since either high school or never? Don't then give it a shot. But if you remember how to find the minimum, remind me how to find a minimum. Take the first derivative and then set it to be 0. So let's do that. Go ahead and do that. I'll do it on the board too. If you have no idea what we're talking about because you never took calculus, sorry. I'm not going to test you on this. Actually, we'll do it this way. Sorry. There we go. Fairly easy calculus equation here, right? Taking the first derivative. Now, remember the first derivative of n over x. We're doing it with respect to x, right? 1 plus, you have to do the business with the subtract from the exponent. It's a negative exponent. Negative nx to negative 2. Set it equal to 0. You end up getting, if you do a little bit more math, that the number of nodes, this was L1, we said was x, right? And we said that L2 was n. The number of nodes in list 1 should be the square root of the number of nodes in the list 2. OK? That will nice and evenly space it out. OK? We could have done it half or whatever. We could have done it a third. But that will nice and evenly space it out. OK? All right. That's all the calculus forever in computer science. Whew. All right. But now you can say you've done it. This is why we make you take Calc 2 if you're a major. I don't know why. I guess. OK. So we do that, and we say, fine. It's going to be when the number of nodes in list 1 is equal to the square root of the number of nodes in list 2. OK? And what does that mean for the actual? So we want them equally spaced, and that's how it actually works out. Basically, you've got the square root of n on the bottom, and because we minimized this, this will minimize the amount of searching you have to do. Right? You go across until you get to a number that's too big, come back 1, go down, and go across until you find your number. OK? That's how that works. Well, this top list up here, it's just another linked list, right? So if it's another linked list, what could we do to the top list? Yeah, do another linked list on top of that one. Another skip list for the, it's like the express for the express, right? The commuter rail or something, like the super express. Right? If we do that, right, if we had more linked lists, so did I not say, yeah, there we go. Sorry, I missed this part right here, right? the search cost is going to be the square root of n plus n divided by the square root of n. And if you do the algebra to figure that out, the search cost is now 2 times the square root of n. Okay, we're not as good at log n yet, right? 2 times the square root of n is not as good as log n, but we're getting there. Okay, 2 times the square root of n is now our search cost. Better than n. Okay, certainly. So we're getting there. We're kind of climbing up. We're getting there. Now, if we had more linked lists, let's say we had a third linked list. Okay, if you had a third linked list, okay, whoops, sorry. If you had a third linked list, if 2 sorted lists is 2 times the square root of n, what do you think the search would be for 3 linked lists? By the way, these other little things on here, because I couldn't get the PowerPoint thing to work right. But anyway, well, if 2 sorted lists gives you 2 square root of n, what's your guess for 3 sorted lists? Yeah. 3 the cube root of n? That's actually absolutely right. You might have thought 3 square root, but it happens to be the cube root. If you do some more calculus, I'm not going to make you do that. Did more calculus, you'd figure 3 lists would give you that, which would mean the top list here would have a search space which is even better. Cube root of n is better than square root of n in terms of number of things you have to search. Okay? What about k lists? Well, k sorted lists gives you k times the k times the, we'll use this in a minute, k times the kth root of n. Okay? And you're like, oh my gosh, kth root, I don't even remember what that means. Don't worry too much about it. Okay? What's the best we could actually do? Right? Yeah. If you had log n sorted lists. Now, remember, Yuki, you'd said, hey, how do you get to log n? Were you the one who said that? Yeah. If you're trying to get a log n, if you have log n sorted lists, you end up with the following. Because we just kind of follow the same pattern, right? Because we had 2 times the square root of n for 2 lists, 3 times the cube root of n for 3 lists, k times the kth root of n for k lists. And if k is in there, then we can put anything we want in there. If we happen to have log n root, whatever that means, of n, right? What does that actually give you? Do you know what log n root of n actually is without looking at the board? Well, let's just figure it out, right? Equals x, okay? If you raise both of those to the log n power, both sides, right? You'd get the log, and we're base 2 in this case, let's say, right? By the way, that's base 2 of n. Log base 2 of n. Log base 2 of n raised to the log base 2 of n, right, equals x to the log base 2 of n, right? What do we actually get on this side? N equals x to the log base 2 of n. Okay, what raised to the log base 2 of n gives you n? 2 raised to the log base 2 of n gives you n. So x is actually 2. So you can actually say that where did I put it here? Equals 2. The log base 2 of n, sorry, I lied, times log of n, times log of n. Okay, log base 2 of nth root of n is 2 times the log of n, which gives us our nice logarithmic behavior. Right? So that's how we're going to actually do this. We're going to have log base 2 of the number of nodes that we have. Have we ever seen another sort of situation where we have the logarithm of the number of total nodes in a system, in a data structure? Yeah? Binary search trees. Binary search trees, remember, if there's n nodes, you have log n based levels in the nodes, right? This is exactly the same thing. Okay, we're really kind of making a linked list it's not a binary search tree, but it acts very much like one. Okay, and kind of looks upside down a little bit. Well, actually, it kind of looks right side up. It's a little bit odd here. But if you have, in this case, 4 linked lists, and you go 2 nodes in the first list, right? 3 in the second, but it probably, yeah, and then 1, 2, 3, 4, 5. If you basically add another one in between every other node, you end up with this kind of more or less binary search tree looking thing. And the way you search through it happens to give you logarithmic behavior. So all of a sudden, we've turned these horrible linked lists into this nice logarithmic search behavior. So maybe there is something good about linked lists. Probably not. But if you make a skip list out of it, you do. Now, what are the downsides to this? It's kind of big, right? There's actually lots of lists going on. There's log n lists of your thing, and you're duplicating a bunch of things, right? You're duplicating all the 50s in there. All the 79s and all the 14s are duplicated in every single list, right? So there's extra stuff there. Yeah? Yeah, if you try to insert, so everybody gets inserted in the bottom list, right? And then you have to figure out kind of how to do the other lists. We're going to talk about that in 1 second. Okay, we're going to talk about a good way to do that. Okay, but in terms of the structure, though, you see how this leads you to logarithmic behavior. If you're searching for stop 59 on this crazy like multi-stop subway system here with lots of express routes, you're going to start at 14. And you're going to look at 79 and go, oops, I'm searching for what? 59. So 79 is too much. I go to the next one, I go to 50. Well, I know 79 is too much. I check that. I go down to the next one. 66 is too much. I go down to the next one, and then I go to 59. So in the end, asymptotically, it's logarithmic. Yes?
Just based on how it's up there, if you don't have a number, like your n is, or x is not, like the square root of it isn't a whole number.
You round. Yeah, you just round down. In the case of like trying to produce one from scratch, you'd have to round down. Question?
If you start deleting elements from the list,
Yeah.
will the spacing sort of degenerate?
Yeah, the spacing would degenerate if you start deleting items. Sure, if you all of a sudden closed stop 50, well then you'd go 14 to 79, and you'd have to skip. You wouldn't get as good behavior, but it's not a terrible thing. Yeah. Sorry.
This might just be because of the size of the example. It seems like we're moving almost as much.
Yeah, it's definitely the size of this example. Yeah, good question. Yeah, it's like, oh, well, look, we're moving backwards and forwards and too many times. Think about this in like a billion, right? I mean, if you've got a billion, you go half a billion, and then basically another half a billion, another, you logarithmically decrease your size like a binary search, because it really is a binary search in the bigger picture. Yeah, you do have a little bit more overhead, but it's basically a binary search. Good. Okay, so that's what a skip list is. Now, the question is, how do you build it? Right? We already know that if you have n elements, you could have log base 2 of n lists. If you know all your elements up front, you can certainly create this by just going through a rote passage of divide by 2, divide by 2, divide by 2, right? I mean, you could do that pretty easily if you wanted to create it. But if you don't know the items that are going in there, it's actually a bit trickier, right? Because if you don't know, how do you know whether or not to put somebody else in the other list? Right? We want to do this in a way that will allow us to make it relatively efficient. Okay? And that's where this coin comes into play. Okay? That's where this coin comes into play. Anybody think about how I might use this coin? What could I do with it, first of all? I could eat it, but I'm not going to do that. Not going to help me create my skip list. Yeah, flip it, right? Okay? We can't keep these perfectly aligned if we don't know when they're coming, but we can do pretty well if we actually use a probabilistic method to do this. Okay? Can't do it perfectly. It's kind of like keeping a perfectly balanced binary tree. It's not possible, right? And there's no real like AVL kind of property to the skip list, right? What we can do is we can flip this coin. Okay? Here's how it works. Okay? There's a little algorithm here. You take your coin. Okay? And first things first, you put all elements in the bottom list. And by the way, we're also going to have, every list is going to have a negative infinity so you know where to start. Because remember how you start in the top left and you go top left down like this. Well, there's always got to be a top left. It would be a little weird if you inserted something and it wasn't the top left. Like you'd have a little trouble. So we're always going to make a top left by saying every list has a negative infinity just as kind of a sentinel for that list sort of thing. It's just going to be like the placeholder for it. You'll see. You'll see how this works. Okay? All elements must go in the bottom list. We know that already. They all end up in this bottom list. Okay? After you insert into the bottom list, you flip the coin. Okay? If the coin comes up heads, that element gets promoted, which is going to happen roughly how much time? How often? 50% of the time. So 50% of the time, you're going to promote it. If you promote it, flip again. And 50% of the time, it will go into the next higher list, and etc. You keep flipping and getting heads until you get tails when you stop. Okay? We're going to actually try this. Who wants a quarter for being my flipper? Nobody does? Nobody wants to flip a, you guys don't know how to flip? Here you go. Good catch. All right. Okay. I don't have another quarter. Good catch. Woohoo. How about this? You can split the quarter with him if you pick out numbers for me to go in the list. Yeah, I'll let you figure out how to do that. Who wants to pick the numbers? Anybody can pick numbers. I don't really care who picks the numbers. But let's pick one. Somebody give me a number. 3. OK. So we're going to start this skip list out. OK, it's going to start out with a bottom level. And the bottom level is going to have negative infinity in it because we need it to kind of have like an anchor point there. OK, we're going to put 3 in there. We'll make it a nice doubly linked list like that. OK, and what did we say that we do? Once we put the first one in there, flip the coin. In fact, let me do this. Let me make this lower so I can fit more stuff on this. Doing this in class, it's completely random, right? So we'll see what happens. OK, negative infinity, and then 3. OK, flip the coin. What did it come up? Not very well. Tails. OK, so we're done. 3 goes in there, and we're done. OK, somebody give me another number.
3.
Not 3 again.
17.
17. OK, we'll do 17. Who said 4? Gonna screw me up. OK, 17 goes in there. Flip the coin. Oh, it came up sideways. Like it landed on the side of the thing. That's not cool. Try it again. Heads. OK, so we actually promote this one, right? We promote this one. We create a new list, right? 17, negative infinity. And we've got that. OK, another number. 44. OK, 44 goes in the bottom list. What's that? Oh, we did flip it. We forgot to flip it again. Thank you. Flip again. Tails. OK, we're good. Lucky. All right, it could have gone up another, which is fine. It could go up another. OK, so we did 44. Flip. Heads. OK, so 44 goes up here like this. And we keep going like this to 44. Flip again. Heads. OK, so we get another one. So 44 goes up like this. We create another list like here, negative infinity, all the way over to 44. OK, flip again. Tails. OK, good. This is actually working pretty well. Let's try one more. Another number. 59. Thank you for doing numbers that are large. They didn't have to be. Right? If you put numbers that are less, we'll do one with less as well. Let's say 59. OK, 59 goes in here like this. Flip it. Heads. OK, we promote it here like this. This sometimes ends up looking like the New York subway. OK, flip it again. Tails. OK, we're good. Let's pick another one that's in the middle somewhere. 7. OK, so 7 is going to go right in here. And we can do that. How do we find 7, by the way? We go here. We go to 44, too big. We go down here. 17, too big. We go down here. 3. 17, too big. It goes here. So you see how you find it? It takes a little while to find it sometimes. But you stick it right in there. And we said 7, was it? 7. OK, flip it. Oh, tails. OK, well, if it had been heads, right, we would have done the same process. But do you see now how this will build this skip list probabilistically? And if you do this if you do this for many elements, right, asymptotically speaking, you end up with a skip list that behaves as if it was properly spaced out. Because really, you want half the elements down here to go in this one, half the ones here to go to this one, half the ones to go up forever. If it keeps on getting heads, then it keeps getting more lists, right? But you're thinking about a big situation here, and probabilistically, the odds are slim that you're going to get more than, say, 7 in a row heads, right? I mean, generally that doesn't happen. So you can, but not, it doesn't happen that often. So it'll grow that way. Do you think you could program this? This is actually a pretty easy thing to program. Okay, all things considered, this is not a hard thing to program. You build a linked list, and you have a linked list class, and all you have to really do is modify that so that it knows how to search through multiple levels, and so that it has links going back and forth from each link could have a link to its equivalent in a lower or higher list. That's it, right? Actually, just a lower list, in fact, right? You never have to search up the list. So it's actually pretty easy to build. You guys could probably build this like, let's say on the final exam, I could ask you to. No, I'm just kidding. But you could build this in like if I gave you a couple weeks to do an assignment, you could build a skip list pretty easily, right? Or a week or so. You could do it pretty easily. Not really a hard thing to do. But it behaves logarithmically for searches, so not a bad data structure. Okay? Questions on that? Yeah, Jeremy. What advantage does it have that a sorted dynamic array doesn't? Well, what do you think? I mean, it definitely allows you to have a node-based structure, right? So you don't have to you don't have to keep doubling. Like we're never doubling the list at any one time. That's kind of nice, right? It's relatively easy to do, although I guess a dynamic array is not that hard. Yeah, I mean, there's probably not that many advantages, but there's you could probably come up with one if you wanted to. It's like I said, it's pretty easy to build, all things considered, and it's logarithmic, and you didn't have to worry about sorting anything either as you go, right? No other real sorting. You basically find the position and it goes there, kind of like a dynamic array, except then you'd have to move all the elements. So probably more efficient to insert in that sense. Yeah. Anything else? Any other questions on this? Deleting a node, you just delete it, by the way. Deleting's easy. Don't need to move elements either. You're just deleting, right? Just delete the node in every list, and it just makes your emergent or your express stops, fewer. That's that. Yeah.
What's the main advantage over like a binary search tree? Just easier to build and easier to balance?
Probably easier to balance, right? Remember how like the AVL tree was not trivial to balance, right? This is by kind of definition balanced in the way you build it. If you do it probabilistically, it's easy to keep balanced, right? Yeah. So, other questions on this? Okay, that's our first esoteric data structure for the day. Okay. Let's look at another one. Totally like scratch your brain of that one. This one's completely different. It's another type of data structure. And by the way, did you skip this in 170, 160?
We had to skip it because of the snow days.
Oh, you skipped it because of the snow days. Well, now you do it in here. You can tell him you did it in 15. He'll go, what? That's my thing. Anyway. OK, so how about Bloom filters? You haven't done those, have you?
No.
OK. Bloom filters are very cool data structure. This is one of those ones that kind of, in some sense, it's a little mind-blowing. You're like, whoa, this is actually, like the answer might not be, like you might get what we call false positives out of this, OK? Which means that you ask for an answer and it tells you and you're not 100% sure it's the right answer, right? This is what this one's all about. You'll see. OK, this is our first probabilistic data structure in the sense that it will give you, you have to figure out a probability of being right or not. OK? All it's used for is to tell whether or not something exists in a set. OK? I put 10 numbers in the set, and I say, is 15 in the set? And it either says yes or no. OK? That's all it does. That's all a Bloom filter does. OK? You can think of a pretty easy way to do that. You could build one of those with lots of different structures. Right? Binary search tree is a good one, or dynamic array, or some sorted array, or something like that. Not a bad way to do a set. But this one is interesting because it's space efficient too, by the way. It's like really small amount of data gives you a pretty big, what we call filter. Okay? Here's this probabilistic part. They can definitely tell you whether or not an element is not in the list or in the set. Okay? If you ask for 7 and it says, no, I don't have a 7, you can guarantee that that's true. If you say, do you have an 8? And it says, yeah, I have an 8. Then you take that with a grain of salt. And you say, OK, maybe I need to check a little deeper if I really care. Sometimes you don't care, right? Sometimes you just only care if something's not in the set. We'll see an example of that in a few minutes. OK, but that's what it is. So this is the probability part of it. It will definitely tell you that something's not in the set. But it won't. It will only possibly tell you whether it is in the set. And you might think that's crazy, but you'll see where we can use this. OK? These are called false positives. See you guys later. These are called false positives. What does that mean? It means exactly what we had before. It says that the element is in the set when it's not. It will say, sure, I have an 8. And that if it doesn't have an 8, then that's a false positive. OK? You do not get false negatives. In other words, you don't say, is it not in the list? And it says, no, it's not in the list, but it could be. OK? There are no false negatives. There are only false positives. OK? If you ever take like a psychology class, you'll learn all about false positives and false negatives and all that. OK? Here's how it works. A Bloom filter has this thing called a bit array. And you don't have to make it a bit. Well, the bit array part is basically a bunch of trues and falses, right? Ones and zeros. We can call them trues and falses. And what they do is you use that bit array to tell you whether or not your element's in the set or not. Okay? And I'll show you exactly how you do that. You can compress these a ton. Bit arrays, because there's only a true-false answer, you can take many, many bits and put them into one single number. Right? You might have to do a little math to get them out of there again, but it's very, very efficient. Right? You can actually compress these guys up to like 32 times. Right? So it's a huge amount of space savings. Okay? Although in general they do need more space than 1 element per bit. You'll see what I mean in a second. Okay. So what does this do for us? Well, here's an example of a bit array. Just a bunch of ones and zeros in this array. Okay? I'll let you worry about, well, you can worry about how to compress them when you get to comp 40. Right? But in this array, let's say there's a 1 and a 0 and a 1 and a 1 and a 1, blah, blah, blah. Like that. Okay? Here's how you do a Bloom filter. Start with an empty array. In other words, all zeros. Okay? And take a bunch of hash functions. So hashing comes into this. Take a bunch of hash functions, okay, and perform those hash functions on some number. So we could have a couple hash functions. We've seen ones like this before, right? You've seen this in the lab, 13 minus the number mod 13 mod 7 for the table size, and 3 plus 7x mod 7. Those were in the lab. If you take 2 of those, okay, they will give you a particular, well, before we get into that, the hash function should be independent. In other words, one hash function should give you a completely random answer compared to the other hash function. Okay, that's kind of a lower level detail, but you need to kind of consider that. Okay, the values get hashed by all the positions, or all those hash values, and then the position, if it's you end up putting a 1 in the position that hash function gives you. Okay? So let's go back to the original again here, the one we had here. So if you do 13 minus the number mod 13 mod 7, and it comes up to be 3, you put a 1 right where that 3 is. So far, so good? And the same thing for the other one. If this one came out to be 6, you'd put a 1 where that 6 is. Yeah? Wouldn't K2 always result in 3?
Yeah.
Yes.
Oh, because of the 7x? Mod 7, yeah, it might. Well, we'll use it. That would be a bad hash function. All right. Well, we'll see how this works out. Yep, it does. OK. So here's your first example. We'll see what happens when you have collisions like this. Actually, as it turns out, nothing happens. You don't care about collisions, as it turns out. So here's what you do. 129, right? And the first one gives you a 1, and the second gives you a 3. So you put a 1 there and a 1 there. OK? And that is for the number 129. OK? And, yep, you're right. Gives you another 3. If you do 483, you put the first hash function gives you a 4, the second hash function gives you a 3. And you just put another 1 there, and this one's already a 1. You don't change it back. You just leave it. Okay? So you do that, and you start doing that. And you start filling in your bit array with a bunch of 1s. If you want to check if 129 is in the table, right? You say, do the hashes again and check those bits. And if those bits are 1, you return 1. And you say, yep, probably in the table. Right? Is there a way for this bit and this bit to be both 1 if 129 wasn't in the table? Sure. If we had some other number that hashed to 1, and we know everybody's hashing to 3, right? But if some other number hashes to 1, right? If we hashed the number 1, right? If we put 1 and 1, if we went to check 129, then it would also, it would also end up showing us that these two are both 1s, and we would report that that other one was in the table when in fact it never was put in there. Okay? So what does that mean? What it means is that you've got this idea that it does it. Now, why do I say there's no false negatives? Could it be the case that I say is some number in there and I get a 0 and a 1 and a 1? Could it ever be that I had put it in there to begin with? No, because we're never changing back 1s to 0s. Right? So if you find a 0 in one of the positions where there should be a 1 for that number, you can say definitely that number is not in the table, in the hash, in the filter. Yeah.
Would you make more than two hash functions?
Yeah, you should make lots. Like you should make many hash functions, like 5 or 6 or 10 or whatever. 3 is a good start. 2's for the example on the board, but yeah, you should definitely make more. And you should make your bit array really big. Not big, not huge, because you want it to be compact, but pretty big. Right? Okay. So if we wanted to check 123 here, 123 goes to 0 and 3. And 0 is a 0. 3 is the 1, because we got that horrible hash function in there. But the 0 and the 1 tells you if there's a 0 there, we could never have put 123 in there. Yeah?
Would it be that the more hash functions you have, the more probability that it's right the numbers in the
We're going to get into the math in a little bit. But you do the more probability, the more hash functions you have, the better in general. The bigger your hash table, the better, right? And there's some other kind of variables we'll get to at the end in here too. All right. Okay. If we look for 100, K1 is 4, and K2 is 3. And look, both. Sorry, I don't know why I have the wrong ones highlighted there. But if you look at 4 and 3. Right? They're both 1s, and therefore you know possibly that 100 is in there, but we didn't put 100 in there, so it's a false positive. Okay? It's kind of cool. Let's do a little example online here. Okay? Why are you yelling at me, calendar? Don't yell at me. Revert server and goodbye. Okay, here's our example. And you can definitely go to this page if you want on when you want to try it out yourself. Okay, so here's what we've got. We've got the ability to enter a string here. Okay, let me make this a little bit bigger if I can. Oh, I can't. Why can't I do this? There it is. Okay, so let's enter a string in here. Somebody give me a string. String. Okay, so we've got two different hash functions here. Right? We've got a 4, one's called FNV, the other's called murmur. They're both hash functions, right? And 4 and 1 goes in there. And do they actually, yeah, and up here you can see the bits we've changed. We've made 1 a 1, and we made 4 a 1. That's the green in there, right? Okay, we've got one thing in the set. Okay, give me another one.
Dedulant.
What is it?
Dedulant.
How do you spell that?
D-A-E-D-U-L-L. That's probably wrong. That's right?
Close enough. All right. So what happened there? We got 3 and 6. So these two are actually completely disjoint from the other ones. So that's nice. We add those two there. Let's add a couple more. What is it? Pancake? C-A-K-E. Pancake. There we go. OK, we add that. Oh, we do have a duplicate there with 4 and the 12. So 4 and 12 is in there now. OK, and there's 3 things in there. Let's add one more.
Waffle.
Waffle. Somebody's hungry. OK. All right, we've got a couple more. So now we've got our our string in there. Now, if you want to check for if it's in there, we can do that, right? The probability, and this is the math we'll go through in a few minutes, the probability of false positive right now is 22%, which seems pretty high when you think about, but remember, we have a fairly small, we only have a 15 element list here. We've just put 4 things in it, right? So let's check and see. Let's check if waffle is in there. All right, waffle may be in the set, right? Because we know we look at 10 and 7 and we go, OK, 10 is a bit set and 7 is a bit set, so it might be in there. OK, let's look for something else. Let's look for some other type of food. Eggs. OK, eggs is not in there. How do you know? Because 0 and 4, it's definitely not in there. And if it says no, we know it's not in there. So that's good. Anybody else? Bacon. All right, I'm going to have to go eat lunch after that. OK, also not in the list because we've got 9 and 8, and 9 is a 0, so we know it's not in the list. OK, you see how this can be useful, right? Let's try to find one that might be in there. Tomato. No. I don't know. Blueberry. No. Oh, we did check that already? Blue. Oh, blue. OK, so blue. Why is that one maybe? Because 3 and 10 are in there. So 3 is a 1 and 10 is a 1. So it's a maybe. Right? Now, probabilistically speaking, 22% of the time, we'll end up with one of these false positives for this input. But do you see how that works? It's actually pretty clever if you want to do that. And it's a very compact structure. OK? No need to go and store extra stuff in there. You're basically just storing a bunch of 1s and 0s in this list. Question? I can give you an example. So it's probably on one of the next slides, but I think it's on one of the next slides. Chrome, the Chrome browser. Okay, if you've ever gone to the Chrome browser, I don't know if you've ever gone to a website, and you go to this website, and instead of the website coming up, it's this red screen with this big loud message from Google saying, don't go to this website. It's known for phishing, or phishing being like trying to get your information from you, not like zzz, It's known for like bad stuff. It's got a virus on it or something. It's known to have that, right? Well, Google wants to tell you whether those sites are bad or not, right? But they don't want to do that by querying some big database every time, because the database is going to be pretty big for all the websites that have bad information in them like that, right? So what they do is they throw this into a Bloom filter, and they throw all the bad sites into a Bloom filter. Right? And if you go to a website and the Bloom filter, your local Bloom filter says, no, that's not a bad site, it immediately takes you there. Why does it take you there? Because it's definitely not a bad site according to Google. Right? I mean, it might become one, but it's not a bad site according to Google, because if it was a bad site, it would show up as a maybe in the list. Right? Conversely, if they do find that it's a maybe, they do go check the actual database. So it saves them the time of checking a remote database. They will check it later. Like if it comes up as a false positive, they go, oh, this might be one, let's check. And the false positives, they check in the real database that have the legitimate, all of them. But they don't have to download that to your computer. See how that works? It's actually a really clever use of it. Did you have something else on that? OK, good. So that's kind of, so there are various uses of this sort of thing. And if you were ever in an interview or something and somebody said, if you wanted to test for set membership, and you ask the question, do I need to know whether it's absolutely in the set? They'd probably say yes. But if they said, why do you ask? And you say, well, because a Bloom filter might be a good idea, then you get the job. Right? All right. So that's kind of the idea. Okay. Let's do a little bit of math. This is not too much, but let's just figure out how they deal with these probabilities. Like, how do they figure out, how did that other site that we just went to tell us that it was 22% likely that we had? And by the way, if we kept adding to that set, right, if we kept adding strings like blueberry and bacon and et cetera, notice that false positives have now gone up to 36. If you keep adding stuff, you're going to get more false positives. Eventually, if every one of these bits was 1, right, you'd have false positives for 100% of the time, right? Well, you'd have it return maybe 100% of the time. It wouldn't necessarily be a false positive. But you got to do we're going to do a little bit of the math to figure this out. OK?
But if it's full, then
Yeah, if it's full,
You're always gonna
right,
have false.
right, yeah, yeah. You're always going to have to check another database if you care whether it's a false positive or not, right, right. But maybe you put so much stuff in there that it just says, please leave the internet. I don't know. I mean, you know, everybody's bad. Question, Jake.
Couldn't you just, instead of saying, just putting 1 over 1 over 1, just add it up, and that way if the numbers don't match up, then you can return this definitely isn't in the list, and that can reduce the chance of a false positive?
Sorry, I'm not sure exactly. What do you say add it up? What do you mean?
So instead of going 1, 1, 1, it goes 1, 2, 3, et cetera, all the way up, and that way you can get something that has like 2 versus 4, and it'll be, oh yeah, this definitely is in there.
Maybe. I'm not sure you're not just creating some other sort of regular set. It might not save you space in that case. The nice thing about this is that it's very compact because it's all ones and zeros. But maybe you might be able to flesh it out a little bit. You'll maybe see a little bit more how that works. Yeah. If we have the number, if m is the number of bits in the array, okay, we have a certain number of bits in that array, right? Probability will tell you that the probability that that bit is not set to 1, if they're random, right? The probability of that bit not being set to 1 is 1 minus 1 over m, because the probability that it is set to 1 is 1 over m, and then not set is 1 minus 1 over m. Okay? If you then apply k hash functions, now remember we said the more hash functions, generally the better, and they should be independent of each other, right? If you apply k hash functions, the probability that the bit is not set to 1 by any of those hash functions is now 1 minus 1 over m raised to the k power, because you've got k ones in there, right? So this is actually not helping you in this case. But the probability is now that you've got the probability of any of those bits being set to a 1. Sorry, the probability of that bit being not set to a 1 is just the number we had before raised to that power. You don't have to write all these down, by the way. There's a 1 at the end. If we have inserted n number of elements, well, each one of those n number of elements is going to contribute to the number of 1s in there, right? So the probability that a certain bit is still 0 is now 1 minus 1 over m raised to the k times n, because now we've added more bits, so there's even less likelihood that a bit is set to 0. Okay? And if you want to know what the probability of a bit being set to 1 is, well, if you know the probability of it being set to 0, you subtract it from 1 to get the probability that it's set to a 1. Right? So you subtract that whole thing from 1, and now you've got the probability that a bit is 1. If you want to test for an element, right, what you have to do is you have to do all k positions that you've now checked, right? And you've got this probability of all k positions being 1, which we had from before. And then you raise that to the number of hash functions that you have, do a little really fancy math, and you end up, this is just a series that ends up going down to 1 minus e, the number e, raised to the negative kn divided by m raised to the k power. This is what you have to take away from this. And I'm not going to ask you about this number, but I'm just saying if you wanted to calculate how many, what the probability is, like they did on the other page, you would do that. You'd say, OK, I have an m-bit array. I've added n things to it, and I have k hash functions. This little one will give you the probability of a false positive. OK? I ran through that pretty quickly, but that's kind of the basic idea. All right? For the previous example that we had, if we had an 8-bit array, and we put 2 things in it, and we only had 2 hash functions, and let's say that we picked a better hash function than the one that always goes to 3, right? Then 17% of the time we will get a false positive. Okay? If you added another element to it, well, that would make this number go up, right? So then you'd end up getting actually a bigger number when you subtract from 1. So you'd end up getting a bigger chance of a false positive. Okay? If you made the number of bits less, smaller chance of a false positive, etc. Okay? Yeah?
So eventually, if you keep adding things, you're going to run into some problems. Does that mean that you would just start like a second?
Yeah. If you don't produce a big enough list to begin with, you're kind of in trouble. Here's the other part that you're in trouble on, right? Right? Well, this is the example we used, right? Malicious URLs. The big negative one here you can't actually delete from this bit array. Because if you try to delete, then you could end up introducing false negatives. Because how would you delete something in there? You'd find all those bits that should be 1s, turn them all to 0s, and then you've broken the whole system. Right? You've broken the whole system by saying now there could have false negatives. And it's probably rare that you'd need both, you'd allow both false negatives and false positives. Wouldn't necessarily do you much good. Right? So you could do that. There are different ways of doing that. You could keep a second Bloom filter of the removals. Then you can get false positive in that one. And then a false positive in that one means a false negative in the other one. And you're in trouble. You probably could just keep a list of the ones you've removed and check against that list if you needed to. But really, you're going to be in trouble. And the odds are good that you have to, if you do need to know in the big picture whether something's in there, you have to keep some other data structure somewhere. Google does it on their server back in wherever, underneath some mountain in Nevada or something. But the bottom line is the Bloom filter is a useful tool, but you have to know its limitations, kind of like all the other ones. There are definite limitations on that. OK? Any questions on Bloom filters? Running time. How do you do the running time on this? What do you have to do to find if something's in the Bloom filter? Bunch of hash functions, and then look up in an array. Right? Through, let's say, 5 hash functions. That's 5 things you have to do, plus a lookup in an array, another 5 things, let's say, for each bit. Easy, right? It's constant. You don't need to know how many are in the entire list. Doesn't matter, right? You need to know your false positive. You probably want to know your false positives, but asymptotically, it's pretty good, right? K, on the order of the number of hash functions that you have, which is generally relatively small. Okay? And if the hashes are independent, this is the best part. You can parallelize them. So if you have a computer that can do like 5 things at once on various processors, throw the hash function into all of them at once, and you'll get the answers back faster, and you've even done better than that. So very fast method, this Bloom filter. Okay? Pretty good data structure, all things considered. Okay? All right. Here's what we'll do. Oh, we still got 8 minutes here. No more questions on Bloom filters? OK, that was esoteric data structure number 2. Esoteric data structure number 3. There's a thing called a rope. Okay, it relates to strings. Okay, strings normally kept in memory in an array. Well, we know that. Well, we should know that by now, right? If you've got a string, let's say we've got the quick fox jumps over the dog. Forget about the brown and lazy and all that. The quick fox jumps over the dog. Okay, and if you put the little underscore there as if they were spaces, this is how it's laid out in the array. Nice and linear in the array. Okay? That's how a string is generally put in memory. The problem with this is, and it's not a huge problem, but if you ever want to insert into an array, you have to find where it needs to go, move everybody over by the amount, and put the new thing in there. Linear type behavior. Right? Not so easy to insert these things. Deleting's the same way. You find where it should be deleted, take all those out, and move everybody else over that many spots. It's just not the most efficient way of doing things. Okay? And we see strings used in many different things. Ever used Microsoft Word? Right? Strings are used continually in that because you've got blocks of text. Right? And I don't know how Microsoft Word actually does this. But one way to do this is to create this other data structure, which is basically like a tree structure for strings. Okay? Here's what you do. You have a tree, and we'll explain what the numbers are in a minute. But you have this tree, and at the bottom node of these trees, you put the various parts of the string. Okay? They don't necessarily need to be the same number of characters. In fact, they won't be if you're inserting like various chunks. If you first started out with like fox jumps over the, and then you added the quick, you might end up with a different like separation of these things. But this is how it ends up working out. Your string is broken down into pieces that go into this odd-looking binary tree. Okay, you get this weird odd-looking binary tree. But it turns out that this makes it really efficient to store these blocks of text. Okay, it's actually pretty cool how it works. Okay? Right? the strings are kept at the leaves. In other words, you've got the strings down here. Here's how these numbers came from. If we had more time, I'd let you try to think about where this came from. But what the weight of each node is just the length of whatever string is at that node, if there is a string there, plus the sum of all the weights in that tree's left subtree. Why does that help us now? If we want to find some position, right, we know that there's 16 characters to the left here, right? And we don't care how many are necessarily to the right, because if we're trying to find position 17 from we're starting at the root, we're going to definitely go to the right. See how that works? And then if you go to, so if you want to find 17, you'd go, OK, I need to find where 17 is. You go here. Well, 17 is less than 24, so I go this way. 17 is less than 19, so I go this way. And 17 is less than 19. Well, I'm going to check right here, because it happens to be the same 19. And I can walk across and find out where 19 is. By the way, if it's 16 here, and I want to find 19, there's 16 on this side, 17, 18, 19. The x would be the 19th one there. See how that works? I'll go through it again. If I want to find the 27th character, I start at 16 and I go 27's bigger, 27's bigger, 27's bigger. Well, I know that it came from 24, so I've got to start at 24, 25, 26, 27. The dog is the 27th character. See how that works? What if we wanted to find, let's say we wanted to find 12. Start here. Where does 12 go? To left or right? Left. How about here? It goes, 12 is now bigger than 10, so we go this way, right? And we know that we are actually, I guess we're actually, if you have to go left, you go, we need to go, we have 6 more from the 10, so 12 is going to be somewhere in this one. And so we've got 10 already, 11, 12 right there. See how that works? That's how these things are like figured out. Okay? So what's cool about this is that not only can you search for things relatively quickly, nice logarithmic type search, right? You can also, so there, yeah, this is the stuff we just went through, right? I didn't really talk about the subtraction part, but you kind of do that. If you're looking for, let's see, looking for 21, 16 is less than 21, so then you go 5. We're looking for 5 more, so it's basically this way and then this way. So we would find it in here. Okay? You can look at these notes a little later. Just want to get through some of this. Okay? Search algorithm, you can look at the search algorithm later, but it's basically enumerating what we just talked about, or rather, writing out what we talked about. Okay? How do you concatenate 2 strings? In other words, add 2 strings together. You don't have to move a bunch of things. You take the 2 strings, or the 2 ropes, rather, which are already in their rope form, right? And you just do this. The time is constant, right? Or I guess n log n, or log n, depending on how far down you have to go. But what you do is you create a new root. The left is S1 and the right is S2. And you figure out the numbering based on that. Pretty easy to do. Okay, pretty easy to do that. Concatenating. What else do we want to do with strings? We might want to split them. How do you split a string? Splitting a string is a little weird, because you have to know where to split it. You basically find the place where you want to split. Let's see, like if we want to split right here at the me, right? What is this? Hello, my name is Simon. Right, if we want to split right here at the me, between the n and in between the n and a and name, we actually have to split this way, because everybody here has to get split. And what you do is you basically split here, and then you put another node here and create a new concatenation there. Pretty simple. Yeah, Jeremy?
If you were actually doing this, would you balance these with ABL trees?
You probably wouldn't bother. Probably wouldn't bother balancing them. It may be a good idea to, but I doubt you'd really want to.
If you were generating them on the fly, wouldn't it like deviate very quickly and get really unbalanced?
Depends on what you're inserting.
Well, if you were just typing into a string and it was...
Well, right. If you're typing into a string, you would need to, right. You wouldn't want to do each one, but you would want to say, you know, I'm going to create a new rope here, and every paragraph, I then concatenate 2 ropes or something like that. Maybe a paragraph is its own rope, something like that, right? Where you'd want to set it up so that you keep it in the big picture balanced. Each individual one might not be quite as balanced as you'd like. But by the way, lots of text editors do use these things as their underlying data structure, because you can do these things so quickly, right? Log n, constant, that sort of thing. Okay? More splitting there. Splitting, splitting. You can also insert, and we really don't have time to go over too much more here. But the bottom line is there are different ways of producing string-like behavior in a non-string fashion that's actually better asymptotically. Okay? All right, that was the 3 big esoteric ones. Don't worry too much about the rope one. We didn't get through all of it. The other 2 you should definitely know more or less for the final. You should know how to analyze them to some extent. Questions? Yeah. Don't worry about going over the notes for the final. I'm not going to ask you about them.